Okay, good.
There's a couple of ways of proving problem one. It is somebody's theorem, and I'm not going to tell you who because then you'll Google it. No, I'm sorry, I wasn't looking at you. But now that you mention it,
I know. That's how I survived.
here's how one might prove that. F prime of A is less than F prime of B. So F, it could be doing something else in the middle here, but at A, most assuredly, F prime of A is that number, and at B, F prime of B is that number. So F prime of B is greater than F prime of A. And what the claim is that for any lambda in the closed interval F prime of A, F prime of B, there exists a C in AB such that when you evaluate the derivative there, it equals lambda. So this is the intermediate value property, which continuous functions have and derivatives have if they're defined, even, right? If derivatives are defined, they have the intermediate value property. And here's how one might prove that. If you construct the tangent at A, of course that has slope F prime of A. And then you rotate this end, keeping it going through the point of F of A until it's in this position as a secant line between F of A and F of B. And once you get it going through there, you rotate it around around the point B, F of B, that's the point, until you have the slope equal to F prime of B. Okay? So it's a two-step thing. I start out this way, rotate it until it lines up, and then rotate it again. So it's tangent at B, comma F prime of B. What's that do? Well, that's a continuous process. Any value between F prime of A and F prime of B will be realized by one of those tangents or secants, right? How do we know that? How do we know that? I think you can use the mean value theorem, which is what this exercise is about. Mean value theorems. Here, let me draw a bigger example so we can see this better. If I have the tangent here, and then I rotate that line as a secant until I get it through the other point, notice that I intersect here, you know, and so forth. Okay? The mean value theorem says that, remember, this function is differentiable, all nicely continuous and everything. So you can apply the mean value theorem to it. There is a value between here and here, such that if I draw the secant through them, there's a point where you evaluate the tangent, the derivative in its tangent. Isn't that what the mean value theorem says? But you'll notice that no matter where this point is here, where the one end of the line is always going through here, the other end of the line can be anywhere up into and including FB. No matter where the point is along the line, I connect the two dots. I can find a value between A and B such that the derivative there is equal to the slope of the tangent right there, or sorry, the slope of the secant. Here's a typical secant line. It has a certain slope. Mean value theorem says you can find a point here so that if you evaluate the derivative, it's parallel to that. Then you can ask yourself, well, what value gets left out? When you do this little two-step process here, the answer is none. You can go all the way from f prime of A to f prime of B and cover every value by picking somebody in between A and B, but that's the thing. That's the biggest thing.